Okay, hi guys. So in this lecture, we'll be talking about some of the differences between a base and a nucleophile, and then we'll be seeing on the nucleophicity of a reagent in polar protic solvents. Okay, so let's start with a comparison of base with nucleophiles. So base on one hand and nucleophiles on other. Okay, so what will happen is, first the base is uh, we have a OH minus and a H plus. The base will attack on here, and in nucleophile we have a OH minus and the substrate is CH3Cl. OH will attack on the positively charged carbocation. So difference is the base donates pair of electrons to proton only. Base donates electrons to protons only, whereas in this case we have that the nucleophile donates its pair of electron to atoms other than proton, and nucleophiles donate electrons to atoms other than proton. Okay, the second point is, let us see this example wherein we have something like this now, and this will actually take up this hydrogen atom. But if you take the same example in this case, this will not happen. Why? The reason is the steric hindrance is less effective in acid base, but steric hindrance is a important thing to be taken care of in case of electrophilic or nucleophilic reactions. So we'll write it that steric hindrance is less effective and here it is an important aspect in nucleophilic substitution. Okay, so you can say that basicity is thermodynamically controlled. Third point is basicity is thermodynamically controlled. And the third point here is nucleophicity is kinetically controlled. So if at this moment of time you are not able to understand these big buzzwords like thermodynamically and kinetically, you can actually ignore them for the time being, and later we can actually discuss it in our physical chemistry lectures, so no need to worry on that. Nucleophicity is kinetically controlled. Okay, some of the example for the same is, we have base plus H plus, so it would form B plus H, and here we have OH minus plus CH3Cl, it will give rise to CH3OH. Okay, so now let us talk about nucleophicity in polar protic solvents. Nucleophicity in polar protic solvent. Okay, so suppose we have RO minus, ROH and So the highest nucleophicity order, or the order of nucleophicity would be something like this. And the negative charge is better nucleophile than its conjugate acid. That negative charge is better nucleophile than its conjugate acid. This was the first example. The second is RS minus is a better nucleophile than RSH. And thirdly, we have this is a better nucleophile than this. Okay, so this was the case 1. This is case 1. We will also have case 2, wherein we will have something like, so if nucleophilic atom is same or the nucleophile belong to the same period, then obviously strong bases are good nucleophiles. Okay, so if nucleophilic atom is same, or if the nucleophile belong, or if the nucleophile belong to the same period, then strong bases are good nucleophiles. Okay, so in this case, if we have something like this, NH4, NH3, S2O and HF, so in this case acidic strength increases in this order. So acidic strength increases therefore this implies that CH3 minus would be a strong nucleophile than NH2 minus would be strong nucleophile than OH minus, and it will be strong nucleophile than F minus. Okay, so this will be the order of nucleophicity. Okay, and second example we can take, like we have RO minus, PHO minus, or maybe, so their conjugate acid order was something like this. So the basic order or the nucleophicity order would be like this. Okay, because the acidic order was something like this, hence the basic order or the nucleophicity order would be something like this. Okay, so we'll be discussing the case 3 and case 4 and the nucleophicity in polar aprotic solvents in the next lecture. So till then, good luck and goodbye.